Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We are discussing phenomenological theories, which we kicked off in the last lecture. So let's briefly recap the idea of phenomenological theories. So typically what we have done so far in the course is we have said that okay, we have to identify some microscopic degrees of freedom such as Ising, spins, etc., and then construct models based on those degrees of freedom. But what we saw in the last lecture was that there are other alternative approaches which are typically motivated by experiments. And what happens in those approaches is you look for some emergent degree of freedom that is that you see in experiments, and it may not be immediately clear as to where those degrees of freedom are coming from. So in some sense we may not know the microscopics that is giving rise to this emergent field, yet we try to write down a theory for such an emergent field, and such an emergent field is what we call as this phi. Okay. Some people call it order parameter field as well, but that can be a little confusing. So the idea is that we reserve the word order parameter for the thermal average of such a field. Right? That is what we mean by an order parameter. It's an observable. This is a fluctuating quantity. Typically phi is that emerges is fluctuating. Okay, the important point about phi is that the phi field that you have identified has to transform correctly under the symmetries of the system. So for example, if we observe the Ising magnet, below Tc you can get magnetization in one direction or the other direction in the absence of any external field with roughly equal chance. So if you do an experiment in one experiment, when you cool it down you may get it up. Next time when you heat it up and cool it back again, it may come back down, and if you do it this many times, it's 50% of times it will be up and 50% of times it will be down. What this is indicating is that there is some kind of symmetry in the system in which you can transform from this up to down, and so whatever this emergent field that you are writing down must respect that symmetry, right, or must be able to carry that symmetry, in the sense that you should be able to act the symmetry operation on this phi to make a transformation. Okay, the next important step is to construct a energy density function or some kind of generalized and free energy density function, something like that, and this is what we call as this Landau function L of phi. Now L of phi has many things in it, as we will see. So one of the postulates of Landau is that this L of phi is taken to be analytic function of all its parameters. Certainly it should be an analytic function of phi because phi is one of the parameters, but L has many other sort of hidden parameters in them. So these could be like effectively the dimensionless coupling constants, and L of phi has to have invariance under the symmetry transformation. As we said that phi can symmetry can act on phi and change phi, and when we change phi in that way, L of phi must be invariant. That is the idea. And the phenomenological inputs that we want to put in are stuff that we know from experiments. So if you are working with Ising magnets, for example, we know that at least in large enough dimensions, if you cool down the Ising magnet, there is a temperature below which you will get spontaneous magnetization. So things like that are known to us. And so what we will try to do is we will try to introduce such coupling constants into this L of phi in such a way that it's all analytic in those reduced dimensionless coupling constants, yet it allows us to see that when we change the coupling constants, the system can actually break symmetry and so on. Okay. So what we did in the last lecture was we used these ideas and we constructed a Landau function for the Ising model, and we were able to reproduce, with the sole input of the fact that there is below Tc there is spontaneous magnetization, we were able to reproduce the critical exponents of the Ising transition, and we found that those critical exponents are same as what we got by doing the more microscopically oriented mean field theory. So in some sense we pulled off a very interesting exercise, in the sense that we put in very little effort to get the mean field exponents, whereas mean field theory we had to solve a set of equations and do partition functions and all of that. Okay, but this naturally raises a question, because we have also seen Ising systems which have a very rich phase diagram. For example, when we discussed the BEG model, Bloom-Emery-Griffiths model, it had a very rich phase diagram with a set of lines of continuous phase transitions, tricritical points, and many other very intriguing and detailed phenomena. The natural question is, how can Landau theory capture something like that? Or is Landau theory just restricted to looking at simple models or simple systems like just a simple plain vanilla Ising system? So this is the question, and in this lecture what we are going to do is we are going to show you that even with the Ising symmetry itself, you can construct very rich and very intricate phase diagrams with the Landau theory. And in fact, you can go very far, even make predictive statements about critical exponents of certain kind, as we will see in this lecture. Okay, so what we are going to do is we are going to now motivate this whole discussion by our study of the Bloom-Emery-Griffiths model, for which we performed fairly detailed mean field theory and we extracted a phase diagram. So let me briefly discuss the Bloom-Emery-Griffiths models to refresh your memory. So it is experimentally motivated by the study of mixtures of helium-4 and helium-3. Helium-4 is a boson and helium-3 is a fermion. If you add very little helium-3 to helium-4, it mixes and you pretty much get the same kind of physics as you would get in the usual helium-4. When you cool down, there is a lambda transition, it goes to the superfluid state, and this is a superfluid. But if you increase the concentration of helium 3, that is the fermionic helium-3, then the lambda transition stops. There is some kind of some tricritical kind of state here, and then there is a line of first order transitions that you will get, and that means you get something like miscibility gap and so on. And this is very reminiscent of like the vapor dome that we see in the Ising model or in the liquid gas transition. So this is our mean field calculation. We saw that in the Bloom-Emery-Griffiths model in zero field, you get a line of continuous phase symmetry breaking, and that is this line here. And then this is delta, so it is not the concentration, so this is some other parameter, and so this whole region is characterized by a first order transition here, and there is this tricritical point sitting out there, right. So this is the essential physics of the, if I want to take all this stuff and make a very simple picture of what we have learned. What we have learned is that there is a system with Ising symmetry, that is the BEG model, which has this very interesting structure. There are two parameters, T and delta. These in a sense are, if you like, microscopic, in the microscopic language. So there is a line of continuous phase transitions that stops at this tricritical point, and then there is a line of first order transitions. This is what we find phenomenologically, right, both from the experiment as well as from some simple minded theory. Okay. So the key points, as I said, there is a line of continuous transitions, there is a tricritical point and a line of first order transitions, and BEG model uses a system with Ising symmetry alone, nothing else. And very importantly, to reach this tricritical point, I have to tune two parameters, T and delta, and also I should not have any external field, right. So three parameters have to be tuned, T and delta have to be tuned to certain value here, and the external field has to be 0, so three parameters are tuned. So this is the phenomenology that we know, and what we want to do is, we want to use this phenomenology to construct a free energy functional. We have to first identify some emergent degree of freedom, etc., and then construct a free energy functional for this, so that we can reproduce a phase diagram that qualitatively looks like this. So remember, I don't have to produce a phase diagram that looks exactly in this shape, right. You can just have, there should be just a line of continuous transition which ends in a tricritical point, and then there is a line of first order transitions. That is all I need. So recall what happened in the Ising model versus liquid gas. In the liquid gas, the first order line in the PT diagram was like a line, and which was curved and it was ending in a critical point, etc. And the Ising problem, where we had magnetic field versus temperature, this first order line was flat and straight and all that. But overall, the structure of the phase diagram there in those two contexts were the same. So what we are really looking for is to find a Landau theory which produces a phase diagram with such a structure that you have a line of continuous transition which ends at a tricritical point and then it continues on as a first order line. So this is what we are after. Okay, I hope the problem is well stated, and I hope that you have already worked out. I had mentioned this at the end of last lecture that you could try this out. So if you have tried this out, and we can exchange notes, so I will show you what I have done and you can sort of check whether this is all okay, or if you have some other ideas, it's very good. Okay, so the first thing is we have to come up with some kind of emergent field. So what I'm going to say is that this emergent field, just like in the Ising model, is some real number, right? It's any real number. And how am I going to implement symmetry transformation? I need to be able to identify a way to implement the Ising symmetry transformation on this. So what I do is I say that if I do an Ising flip transformation, then under this transformation, this phi will get mapped to minus phi. Since it's a real number, the notion of minus phi is well defined. So that is very clear, hopefully, right? And now I'm going to write down a phenomenological functional, phenomenological function for phi, L of phi. And what I'm going to do is, I realize that I cannot do anything with phi to the 4, because phi to the 4 I have already explored. So what I'm deciding to do now is I'm deciding to keep one more power of phi. And remember, we cannot keep any odd power of phi, because that will not respect this invariance of under this symmetry, right? So now I have introduced 3 power, phi square, phi to the 4 and phi to the 6, and I need some coefficients in front of them, right? I need those functions which are typically functions of temperature or some other parameter. So in this case, we know that we need to be able to tune two things, right? So we needed, for example, if I didn't have any external field, I had to find Tc and delta C to get to the tricritical point of some sort, right? So what I'm going to do is, I'm going to say that there is a coupling constant multiplying phi square, and this I'm going to take as dependent on some dimensionless temperature, if you wish, right? So this is AT, little t is again that distance to the transition, T minus Tc by Tc, and I'm going to introduce, this is new, I'm going to introduce a new parameter, again some dimensionless coupling constant, U, such that this is some distance to transition to the other object, something like delta, right? So I could think of it, if you want to make a direct connection to Bloom-Emery-Griffiths, you could think of this as delta minus delta C by delta C, something like this. So bottom line is, since I need to tune these two parameters in the absence of a field, I am going to introduce two dimensionless coupling constants in my phenomenological theory, right? So I'm using that experimental fact or the numerical fact, either way, to construct this. Okay, so I'm going to say that T can go from positive to negative, U can go from positive to negative, and this G, I'm going to be taking it as a constant positive number. So in the way I have written this down, right, A, B and G are all positive quantities. Now you may wonder, how do you know about what is A, B and G? Well, you don't, right? In fact, I will argue that you can actually always choose A, B and G to be unity. So let me give you an argument for that. So first, G is a positive constant. So I can actually redefine my phi by multiplying it by, say, G to the power 1 by 6. So I get a new phi, and so that will just change the definition of phi. But phi is completely within my within my grasp. I can change the definition of phi. I can just scale phi by some number. So I can get rid of this term, and then you see this symmetry operation will still be valid, right? Because if I add the symmetry on phi, the new phi will go to minus phi. So I got rid of this G. What do I do with this? Okay, so when I do this, I have to get some extra factors of G and all here. So let's say I get all of that stuff, And then what I can do is I can multiply all of these things together and define that as a new u, right? Because if it is t, if I have a t, I could just scale t by some set of numbers, and that is not going to change the qualitative aspect of the fact that this t changes sign as I move the value around, right? So I can still make it change sign. So similarly, what I can do is I can put this all in here, and I can construct it in such that this absolutely looks like t by 2 phi square plus u by 4 phi to the 4 and just 1 by 6 phi to the 6. That's absolutely fine. There is no problem with that. But let's hold on to these constants for now. Maybe we can, if you want to connect up with experiments and you want to choose certain dimensions for L of I, right now the L of I has dimensions of just 1 by volume, so it's like a density. But suppose you want to choose later, as you will see, you may want to choose it to have some other dimension, then maybe we can use this A, B, the freedom that we have here in choosing A, B and G and all of that stuff, and we can try to make some progress as required. So with that comment, this is the my claimed Landau functional that will produce all the Bloom-Emery-Griffiths physics. So let's see how that works out. Okay, so like I said, there's two tuning parameters t and u are akin to this t by j and delta by j of the BEG model. Okay, all right. So let's make sure that everything, the Landau function we have written down has all nice properties. So it's clearly analytic in all the parameters that are there. It's analytic in t, it's analytic in u, a, b are just constants, g is a constant, phi square, all these are analytic terms. So it's a very nice analytic function of all the parameters that we are using, right? Okay. Second is, by construction, L of minus phi is equal to phi. This is very trivial for you by now. It's obviously satisfied. And if I have an external magnetic field, then I can simply change this L of phi by taking this original L of phi and just applying, just writing the interaction energy of this field phi with respect to the dimensionless magnetic field H tilde. Okay, so this is the idea. All right. Now, important question is, how does this get us all the physics that we are looking for, right? Okay. So first, what we will do is we will study this problem by setting u to be a positive number, right? So if u is a positive number, you can see that this quantity is bu is positive and g is already positive number, and at phi square plus some positive number phi to the 4 and phi to the 6. That's what we have. Okay. So now you will see that if u is chosen to be a positive number, the physics will be exactly same as what we had in our original, the simple Ising model, which was just at phi square plus b, no u dependence there, b was a positive number, divided by 4 phi to the 4. And we got that when t becomes negative, you have a broken symmetry phase, and t equal to 0 is a critical point. So what you will now find is that you will find exactly the same results, except there will be some small numerical corrections coming from the phi to the 6th term. Apart from that, all physics is the same. There is a continuous phase transition at t equal to 0 for any positive u. This is the statement. There is a continuous phase transition if you fix u positive and change t, as t hits 0, there is a continuous phase transition at that point, and then if you reduce t to negative values, it breaks symmetry and so on. So what we have just discovered is that this model, as we have stated in the previous slide, has a continuous line of continuous phase transitions. What is that line? The line is simply u equal to 0, u greater than 0 and t equal to 0. That line is a line of continuous phase transitions. Okay. Now, that is a very interesting observation, but there is something more interesting that you will find if you look at what happens when u is less than 0. When u is less than 0, now there is something very interesting that will take place. You see, so as a function of phi, this quantity for t positive, let's say, this quantity will give you a positive contribution. This quantity will now start giving you a negative contribution, and this quantity will always give you a positive contribution, whatever be the sign of a, t and so on, right? So you will start getting some kind of competition between this negative contribution and this positive contribution, etc. Okay, so this is what is going to happen. So let me show you in a graph what actually happens. Okay, so what I am going to show you is that the transition as a function of t, when you reduce t when u is negative, you start from t some very large positive value and start reducing t, you will have a transition, but that transition will be first order and it will occur at some value of t, which we will see presently what the value of t, where a first order transition occurs, and that value of t, which I am calling tf of function of u, depends on the value of u that you have. If u is very large and negative, then you need a larger, you will find that tf will be larger. Okay, we will see that. Okay, but let us see how this works out. Okay, so what happens is, I have some u set to be -1 in this calculation. Okay, so this is the calculation, and you will see that because I have that negative 5 to the 4 term, as I am increasing phi, this thing simply does not continuously increase. You see, the effect of phi, the negative 5 to the 4 term starts to come to play when phi becomes large enough, and it tries to slow down the growth of this function. Of course, if you eventually take phi to very large values, the phi to the 6th term will take over, and it will just all go to very large values anyway. Okay, so that is always going to happen. But what you will see here is that the phi to the 4 term takes effect, and the point is, as I start reducing t, a particular value of t will come when you see this thing will develop a well defined local minimum, right. So the derivative of the L of phi will vanish at these points. So these are some local minima, to the point that you can reduce t equal to tf, and you can see that this green line here is slightly thicker than the other line, and that line is the line where t becomes equal to tf. And now you see something spectacular happen. You will see that the energy of this the Landau function L of phi at phi equal to 0 has 0 energy. That is exactly this point here which I am showing, and there are two other values of phi at which the energy is 0. That means there are two states with coexisting energies. Where have we seen that before? Whenever we have a first order transition, there are two states with equal energy, right. And this is exactly what happens when t equal to tf. Three values of phi have the same energy, namely this minus value here, the 0 value here, and this positive value here, right. And therefore, we say that the system will spontaneously choose either this or that, and if you reduce t, it will fall into one of these wells, if you like. And therefore, as I change the value of temperature little t from, and when it crosses below Tc, the equilibrium state which was the lowest energy state for t greater than tf, which was at phi equal to 0, changes abruptly, discontinuously to a value set by some number here. Okay, and this is what gives rise to the first order transition. Okay, now how do I find out at the value of tf, right? So that is a very interesting calculation, and I strongly recommend that you do this. I will indicate how this is done in this discussion. So what you realize is, at this point where at the value of tf where this first order transition takes place, the value of L of phi at the place where this L of phi curve touches the 0 line is 0, of course. And that is saying that this state at phi equal to 0 and the state where this touches the 0 line have the same energy of 0. So you need to impose this condition that L of phi equal to 0. But it is also true that the derivative of this phi vanishes here, derivative with respect to phi of L of phi vanishes here. Okay, and you solve this, and that is the condition for the second condition. And what you will have to find is, you will have to find a solution of phi which is non-trivial. Non-trivial means non-zero, right. So whenever there is a non-zero solution of phi, you will be able to get these two conditions, and you can eliminate that elimination in mathematical sense. You have two equations with which have to be satisfied by the same variable. So that means that the rest of the variables in that two equations, the rest of the quantities are constrained. So that constraint will give us the condition for the first order transition, and you should be able to show fairly easily that the first order value of tf is this quantity which is proportional to u square, and these are all some numbers, the b square by ac and all that. Okay, so that is the number. And what we now see is something very beautiful, which is that this kind of first order transition will exist whenever u is less than 0. Okay, so whenever u is less than 0, I have a line of first order transitions, and the line is described by u less than 0 and tf equal to this. Okay, so this is what I find. Okay, so now let's put this all together and let's try to find out a phase diagram of the system when there is no external magnetic field. So what does the phase diagram look like? Okay, so what I have done here is I solve this equation dl by d phi equal to 0, and the value of phi for any set of parameters that I have that solves this equation will be my spontaneous magnetization, right? And so what you find here is this x axis here is u and the y axis is t, right? And you see this very nice result, which is that when u is positive, when t is positive, the spontaneous magnetization is 0, right? And that is this region of the 3D plot. So these two plots are the same thing. I am just plotting this just to show you the contour plot here and the phase diagram. And this is for you to get a feel of the magnetization as a function of t and u. So this sort of greenish region here is this this flat 0 region here. So just as we promised, when u is positive, if I reduce t, I will undergo a first order transition, and here I am doing this. Here if I go this way, I am reducing t and I start developing an order parameter below t equal to 0, and I will go into the usual, so whatever we saw in the Ising model kind of story. Okay. Now what happens when u is negative? This is what we had discussed in the last slide. So when u is negative, I come down, as I reduce t, I encounter a first order transition. That's where suddenly it jumps up and it goes up. There's there's a cliff like thing in this plot here, and that is the sudden change of colors, as you can see. And this curve that is plotted here is the line of first order transition. So this is the tf equal to u square line. So that is that line. Okay, all right. So the key features are, there is a line of first order transitions for u less than 0, there is a line of continuous transitions for u greater than 0, and there is a tricritical point at u equal to 0 and t equal to 0. Okay. So now you can see that this picture has the very same structure as what we found in the BEG model. There is a line of continuous transition which stops at a tricritical point, and then it sort of takes off as a first order line. Okay. So we have actually recovered the physics of the BEG model in a Landau framework, and you can just imagine how much technically simpler the Landau approach is, and we put in very little information. All we put in was the fact that okay, we have this line of phase transitions, etc., and we are able to sort of reproduce that stuff. Okay. So as of now, we have not achieved anything spectacular. We have just reproduced the data that we have done, that we have seen before, in some framework of the Landau function. So let's see what else we can pull off. Okay. So now the natural question to ask is, what happens if I apply some external field? What is the new physics that I can see here? So remember what happened in the BEG model when I applied an external field. So what happens is, if suppose u is greater than 0 and t is varied, if h tilde is non-zero, then it's like the standard Ising model, and then you will not have any phase transition. Your magnetization will simply continuously change as a function of t. Right? That's exactly what happens here as well. So you see, this is u positive, and I am just u positive, and I am starting from some large value of t. There's very little magnetization, and then as I reduce t, the magnetization increases, and that's going along this curve on this, in this sort of surface plot. So you see that the line of continuous transition has simply been wiped out. Okay. Now what happens when u is negative? So let's say u is minus 0.15, so it's somewhere here, and I start here. I am in the symmetry unbroken phase, and so that's somewhere here, and I'm coming down in temperature and I hit the first order line and I just climb up the cliff and I go here, right? So that's this point, and I now have an order parameter which is non-zero. So now the most interesting thing that comes up is that this first order line actually terminates at a critical point Tc and Uc which depends on H tilde. Okay, and that point is somewhere here, right? So that is the point where there is a change, but it's the termination point of the first order line, and that is what is shown in this light blue color here, right? That is this Tc and Uc of H tilde. So what is the statement? The statement is that if you take the slice of the phase diagram at any finite H tilde, there will be a line of first order transition which terminates in a critical point, typical like critical point of the Ising kind, right? And so what I have done here is I have shown you that even for a very, very small magnetic field, this critical point shows up. Okay. Now, how do we find this Tc of H tilde and Uc of H tilde, etc.? Okay. This is a very interesting exercise. Again, I will invite you to work all this out. So you will realize that this critical point can be found by the following set of conditions. So you have three parameters entering the calculations now. There is T, there is U, and there is H, right? And there are three conditions that have to be satisfied by the same phi, right? What this will force is, it will force that two of the parameters, namely T and U, will depend on H, and that is the point. Okay. Now, what is the motivation for making these conditions? So, L tilde phi by L, so this L here should be L of phi and H tilde, remember, okay. So, this is the L of phi and H tilde, so it has to depend also on the magnetic field, right, okay. So, you have to solve that. That is simply the condition of the magnetization, being the condition for magnetization connected to the magnetic field. This one says that its second derivative has to vanish, which means it's like some kind of inflection point and so on, right. So, these are the conditions of it being some inflection point, and third derivative also vanish. So, it's as if like two solutions are meeting in a sense, right. And if you work all the details out, you will find that Tc of H tilde goes as the fifth power of H tilde to the 4, and Uc is negative, that is perfectly expected because we know this happens only for negative U, is fifth power of H tilde square. Now note that these results don't depend on the sign of H tilde, and that is exactly what you expect because of the underlying Ising symmetry. So what it does, yes, if you apply magnetic field in one direction, certain spin is polarized or spins aligning with that magnetic field is favored, sure, but the energy gain in that process should be exactly same as even if you apply the magnetic field in the opposite direction and the spin aligning in the opposite direction. That comes from the underlying Ising symmetry. So the answer should not depend on the sign of H, and they don't, which is a very, very reassuring result. So these are the results that we have for Tc and Uc of H. And now what we can do is we can take all of these results and put them together and make a three-dimensional phase diagram of our BEG inspired Landau theory. And this is the phase diagram in the U, this is the U, T, H space, right? H tilde space. So this is what we have. So this is U, say x-axis, y-axis and z-axis, right? U, T, H space. Okay. So what are the things we see here? Okay, let me explain this. The key features are the following. There are blue lines are lines of continuous phase transitions. So let's understand what these continuous phase transition lines are. This line, this continuous line which is ending in this magenta point here, which we'll discuss in a moment, this line is the line of continuous phase transitions we found when H tilde was 0. So this is on the H tilde 0 plane, and that's our usual Ising like transition going down that, right? And you see this continuous line of continuous transition are the TC and UC as a function of H tilde that I was encountering for any finite H. So if I cut this system at a finite H, if I cut a plane through this, you will see that it will hit this surface, okay, and then it will also hit this curve at some point, and that is the critical point on the plane at finite H tilde. Okay, so these planes now are the planes of the first order transitions. So let me remind you a simple first order plane that you already know very well. So if you say u is greater than 0, then we know this problem is exactly like the Ising model when u is greater than 0, right? So below TC, you have this first order plane. What is that plane? That is the, if I have a positive magnetic field, all the spins will be aligned in the positive direction. And if I have negative magnetic field, they'll be aligned in the negative direction. And if you go along that perpendicular to that surface, you will encounter a first order transition. So this is the usual Ising first order line, if you wish, below TC, right? Below T equal to 0, little t equal to 0, right? So that is that plane. What are these first order transitions? Those first order transitions are exactly this, it's the locus of these lines, right? So as I am changing H tilde, those first order lines are sort of moving in that space of T, U and H tilde, and they will span out this surface. So that's this first order surface, and there is a mirror image surface on the other side because of the Ising symmetry as we discussed, and you will see that there is the other line coming from on the negative of second order transition lines that goes up on the other side. So these lines are the first order transition lines. Okay, now what is this red line here? The red line here was the first order transition line on the H tilde equal to 0 plane. But now we understand that it is more than just the first order transition line. It is indeed a first order transition line. It's actually a line of triple points. Why triple points? Because along this line, three phases, if you like, have same energy. So this has no spontaneous magnetization. This has negative spontaneous magnetization. That has positive. This side has positive spontaneous magnetization, and that side has negative spontaneous magnetization. So all these three phases coexist along this line of triple points. Okay. Now the remarkably beautiful thing that comes out of this is that this line of triple points ends where these three lines of continuous phase transitions meet, and that point is the triple point. I'm sorry. That point is the tricritical point of the problem, right? So this is a critical point and it's a tricritical point, and to get to the tricritical point, I have to tune three parameters, T, U and H tilde. So the line of triple points ends at the tricritical point. Okay, and these are all first order phase boundaries. The surfaces are first order phase boundaries between different phases and so on. So we get this remarkably rich and beautiful phase diagram, which we have calculated using BEG before, right? So that is it's very similar to that, right? So you may think, okay, this is great, but you see, didn't you actually just put in the answer by knowing the phenomenology? Yes and no. So yes, I put in the phenomenology, but I found all this stuff about triple points and all this, So that I didn't put those in, but that did come out. Okay. But I am going to show you that we can actually say something which we have not put in at all, which is the physics of what is happening near the tricritical point. And so this is what I am going to show you in the next couple of slides. Okay, so let's discuss tricriticality. Right? Tricriticality is where I have a critical point where I have to tune three parameters to attain the criticality, and so I have to set these three things equal to 0. So now what I could do is I could move around near the tricritical point and I could look at how are my properties changing. For example, is there some kind of divergence? How is the non-analyticity of the free energy affecting divergences of variety of quantities, etc. In particular, are there tricritical critical exponents, right? Okay. So what we are going to do is, we are going to move in the direction where I keep u equal to 0 and I vary t, right. So in this language, what I am going to do is, I am going to keep u equal to 0, so u will be kept 0 here, and I am going to vary t. So in some sense, I am going to go vertically in this picture like this, right. If you want to see this in the 2D picture, what I am going to be doing is, I am going to try to move along this line, right. So that you can see that that 2D picture is actually same as this 3D picture, right. So I'm going to move along this direction. So I'm going to keep u equal to 0, right. So that's u equal to 0, and I'm going to vary t. That's what I'm going to do. Okay. All right. So let's see what happens. So what happens when t is varied? Okay. So if I want to find anything in this problem, I have to find, take the Landau function which depends on the magnetic field, take its first derivative, equate it to 0, and I will end up getting this equation, and this equation will tell me, the solution of this equation will tell me the magnetization if I have any h tilde and whatnot, right. Okay. Now, how do I get spontaneous magnetization? Spontaneous magnetization you can obtain by simply setting h tilde equal to 0 and solving this equation and asking, are there non-trivial solutions for this equation even when h tilde is non-zero? And you will find, quite analogously to what we did in the usual Ising model, that indeed this equation has non-trivial solutions when t is less than 0. So m of t will be 0 when t is greater than 0. Remember, u is set to be 0 here, and this, you will see the magnetization. You can see, I can pull out m, since I am looking for a non-zero solution of m, I can cancel m. So at plus g m to the 4 equal to 0, and the solution of that is what I am finding here. And therefore you will see that the magnetization will vary as distance to the transition to the power 1/4. So now we have found a new tricritical exponent, beta, which is 1/4. So we are saying that if you tune the system, one parameter u is tuned to tricriticality, and if you vary t, the magnetization will behave differently from what we had in the usual Ising critical point. So beta is a tricritical exponent, and you can see that the amplitude ratio, because magnetization for t greater than 0 is 0, this amplitude ratio vanishes. That's not too surprising. But beta 1/4 is something that the theory is giving you as a prediction. Okay, we can now look at the thermodynamics. So if I look at the free energy of the system when h tilde equal to 0, so I am looking at the plane where there is symmetry in the system, there is the Ising symmetry, you will be able to show after a little bit of calculation that the free energy as a function of t, remember u is set to be 0, right, this whole discussion is taking place when u equal to 0. F of t will be 0 for t greater than 0, and it will have this particular form where it goes as mod t to the 3/2 for t less than 0. So from here you can do a very straightforward calculation, and you will find the leading divergence of the specific heat goes like this. So specific heat is 0 for t greater than 0, right, and it is 1 by square root of mod t for t less than 0. So we now have a very, very nice result which says that the specific heat critical exponent alpha is 1/2 from the Landau theory, and this amplitude ratio C alpha plus by C alpha minus vanishes. Okay, that's because specific heat here for t greater than 0 is 0, right. So this is also a very nice prediction. Okay, all right, we can do more, so let's do it. So we can find out what happens to the susceptibility. So how do we do susceptibility? We want to understand the susceptibility in zero field. So the way we play this game is, we find the system, we don't apply magnetic field, the system may have spontaneous magnetization. We apply an additional magnetic field now and then see what is the change of the magnetization. So m in this set of, in the m here is the magnetization that is spontaneously generated. So when I apply the field h tilde, it produces some response delta m, and therefore the equation that I need to solve is at m plus delta m plus g times m plus delta m to the 5 equal to 0, and this if you linearize in delta m, you will end up getting this expression. Okay, all right. So now from here I can pull off the susceptibility, and you will see that the susceptibility has chi going as 1 by t for t greater than positive, for t greater than 0 for t positive, and 1 by mod t with a factor of 4 for t less than 0. So you will see that this produces exactly the same critical exponent gamma equal to 1 as we found for the usual Ising model, right? Ising model meaning the usual Landau theory which we use to model the Ising system, right? And the amplitude ratio though is different, it is 4 instead of 2, okay. So this is the difference. And there is one more interesting difference. So what happens at t equal to 0, there we can see from this expression that there is no linear response, right. So because m is equal to 0, at equal to 0, so this whole thing is gone. Since m equal to 0, g times delta m to the power 5 is h tilde. So this equation does not apply now because you cannot linearize. There is m, you can't pull, there is no finite value of m, so you can't do this. And so you will get g delta m to the power 5 is h tilde. And therefore delta m now will be h tilde by g to the 1/5. So this gives us a tricritical exponent delta equal to 5. So starting from the BEG phenomenology, we constructed the overall phase diagram, we got all the essential physics of the BEG kind of system in our Landau theory. But we also found some very interesting new results which are the critical exponents at tricriticality, right. Okay, so let me summarize this lecture now. So we will just revise what we do in Landau theory. So construction of Landau's phenomenological theory begins by identifying some kind of emergent field phi that transforms correctly under the underlying symmetry. You can define the energetics of phi by defining some Landau function. And Landau function has to have analyticity and invariance under symmetry, and most importantly Landau function has to be constructed to respect the phenomenology that we are trying to capture. So in some sense you will introduce some dimensionless parameters in the Landau function, and varying those dimensionless parameters will give rise to different phases and all of that stuff, right. So for example in the BEG theory we introduced 2 dimensionless parameters, whereas in our original Ising discussion of the Ising model, we had just a single dimensional parameter which was t. Okay, now I want to make a very important point here, right. So it's very important to understand that the word analyticity is used in slightly different ways here. So the first thing is that we claim that L of phi as a function of phi and the parameter should be analytic, right. But remember, the phase transitions occur because of non-analyticity of free energy. So the relationship between L and free energy is, you have to understand that L is not same as the free energy of the system in equilibrium, right. L is some energetics associated with some field phi. It's analytic in all its variables. The free energy is the minimum value of L as you vary the different dimensionless coupling constants, etc. That's what will give you the free energy as a function of the coupling constants. That free energy, which is the minimum value of L of phi, is non-analytic in the parameters. So this is the main idea. The equilibrium free energy density turns out to be contain non-analyticities which captures the phase transition. So you start with something, some quantity L of phi which is analytic in all its parameters. You find its minimum value when you vary those parameters, and that minimum value as a function of those dimensionless parameters is not analytic, and this is what is giving us all the phase transition physics. So it's a very clever way of capturing a phase transition, to say the least, right. And it is an extremely powerful tool, and as we go into the course you will realize that it is actually a very deep idea that is contained in this Landau framework, and it in fact is actually a paradigmatic way of doing, it's a paradigmatic idea in physics. It's called as the Landau-Ginzburg-Wilson paradigm, as we will see later. These ideas are used extensively in modeling a variety of systems, and main thing is we have to use this judiciously, exploiting all known phenomenology and constructing Landau functions that respect all the known phenomenology as well as ideas of analyticity and symmetry. And like I pointed out, we have seen that Ising model and the BEG model both have global flip symmetry, yet you can produce different phase diagrams as shown in the last couple of lectures. So I hope you are finding this Landau theory and the idea of phenomenological approach is a really rewarding and interesting way to think about physics problems without worrying too much about the microscopic details. And we have so far discussed systems with discrete symmetry like the Ising system, etc. So you may wonder, like, how will you apply this to a system with continuous symmetry? And a very nice example of a system with continuous symmetry is the superconductor or superfluid transitions, which we have discussed in a couple of lectures back. And in the next lecture, we will start the discussion of how we apply this Landau theory to systems with continuous symmetry. In particular, what we will be after is, we know Landau theory can give us critical exponents. We would like to know how the critical exponents depend on symmetry. So we know, for example, in experiments that the critical exponents for different symmetries, systems with different symmetries are somewhat different. So can we extract from Landau theory the differences in the critical exponents that will show up because of the differences in the underlying symmetry? So I'm sure this is an intriguing question for you, and I look forward to seeing you in the next lecture for that discussion. So see you.